Okay, no, AIMPLAS is not a group of projects, it's a research institute, and I will introduce 5 of our projects, 4 of them running and 1 finished project. I have 8 minutes per project, so I will have to be very fast. We will pass this. The only thing I want to mention about the Institute is that we are active in research, but also in services and training. And this, we started with European projects in 2000, and since then we have been participating in 65 European projects. 24 are ongoing, and 11 of them are coordinated by the Institute. So, first project, NATEX. NATEX is based on natural aligned fibers and textiles for use in structural composite applications. Here you have the consortium. And this is the main data of the project. We have a budget of around 4 million euros and a funding of the European Commission on the level of 3 million euros. It's a 42-month project, and we are at the 29th month. We have 17 partners, and you could find much more information in the website, and I think we have flyers outside. So basically, we work in this project in the fibers, in the resins, in the way we produce the fibers, and we modify them to improve the compatibility between the resin and the fiber, in the production of the components, and of course in fitting the application requirements. The idea is to develop an innovative chemical and enzymatic treatment to improve fiber matrix adhesion, specific treatments of the yarn, chemical and natural, and new methods for low twist yarn to improve the yarn mechanical properties and the fiber matrix impregnation. Intermediate materials to improve fiber matrix ratios, and development of new weaving technologies for improvement of the impregnation of the fibers. Also, we are working on 3D textiles. We also have a line of the research in working on reducing, controlling, but mainly reducing the viscosity of the resin using thermal conductive additives, allowing a lower processing temperatures in order to reduce the degradation of the fibers. Increased compatibility with natural fibers by using coupling agents and surfactant additives, and material adaptation in order to fit all these in the traditional composite processing technologies. These are some of the applications. We have a case study on transport systems, agriculture equipment for tractors, energy system for solar installations, and shipbuilding. I have samples of the other projects, but as I came with Ryanair, it was impossible to come with them. So the workflow, we work in Finland. Our partners there, VTT and Alto, work in the fiber modification. In Poland, the Textile Institute work on yarn manufacturing and fabric development. We have other groups working in the polymer selection and modification. And then in our institute, we work in the processing optimization. Thermoplastics used were PLA, PP, and PET, and the thermosets were polyester, epoxy, and furan resins, and also furan prepregs. We have furan resin manufacturer in the project, Transfuran. We produce 3D fabrics, blended fabrics with commingle process, 2D fabrics and prepregs. In the process development, we work in infusion and in continuous compression molding. These are examples of the prepregs. And these are some of the components. We obtain very good surface results, and also the mechanical properties were quite adapted to the application. So the main achievements, spinning process into yarns, improved compatibility, different architectures. The use of these thermal additives allowed us to reduce more than 20 degrees the processing temperatures. So this is related to the NATEX project. BUGWORKERS is a completely different concept. In this project, the idea is to produce PHB-based nanocomposites for high-performance applications produced from environmentally friendly production routes. In this case, our source is forest waste. So it's from vegetable source, but is not from crops, but from the forest. We are aware that one of the main problems we will need to solve is the low yields on the production and the small processing window, so it's not easy to process the PHB. So in this project, we want to develop new low-cost, competitive, tailor-made materials for environmentally friendly production routes. We will work on PHB matrix and lignocellulosic nanofibers. And the idea is to be a real alternative to existing engineered polymers, such as polyamides and ABS. So in this project, we are working for two final markets: household appliance and communication devices. The way to improve the yield is through the density of the fermentation cultures and the new hydrolyzed sugars. We started this project 1.5 years ago, I think, and we are in this stage of the project. So we have no samples because we are still working on the cultures and the right formulation of the sugars in order to increase the yield of the PHB production. We will produce two grades of PHB: a homopolymer with highly crystalline and high thermal and chemical resistance, and a copolymer with improved flexibility and impact resistance. At the end of the project, the idea is to obtain blends of these two grades in order to fit the properties of the different end-use applications. On the other side, we will develop functionalized lignin-based nanofibers and cellulose whiskers obtained through enzymatic treatments from renewable resources. And, of course, the compounding and processing technologies will be focused on reducing the material degradation and improving the end product properties. So, in the presentation you receive and you have in the memory stick, you have more detailed information. I think I have no time, but all the objectives of the project were quantified. We want to increase at least in 30% the yield of the PHB production. We want to reduce in at least 70%, and with the studies we did previous to submit the project, with the people working both in the sugar production and in the PHP production. We believe that we will reach this 70% decrease in the cost. And we also need to increase the processing window for PHP. So these two ways of obtaining the homopolymer and the copolymer, and then to obtain blends to fit the needs of the different applications, we believe that are the route to obtain this increase in the processing window. The nanoparticles will be also produced in the frame of the project. The compounding of the PHP and the nanoparticles will be done using a planetary multi-screw extruder. It's an equipment that allows to obtain a very good dispersion of the particles, could be nano or not, but with a low shear rate. In this case, we obtain a good dispersion with a lower degradation when we use natural fibers, in this case, biopolymers. The idea is to introduce the suitable couplinations by reactive extrusion to improve compatibility, and to also reach higher fire resistance and thermal resistance of the composite. The final composite our aim is to reach something close to 100%, but as explained the previous speaker, as closer as possible to 100%. We are not sure if it will be 98 or 9 or 5. And in the project, we will also work on multi-layer structures in order to obtain multifunctional material properties suitable to replace the engineering materials. This is the structure of the project. So first, the definition of the properties we need for the application, then development of the nanoparticles and the polymer, the preparation of the compounds, and then co-extrusion of the different multi-layer structures to produce the case studies.